Hey everyone, Dave here again. This mini lecture's on SI units. The SI unit system is an international system of units. The term SI is derived from the French, Système International des Unités. The important point here is that it is an international system and it's used in pretty much every country on the planet. And in science. The system's based on 7 what are called base units and the number 10, and you're already familiar with it to some degree because the metric system is based on the SI system. What we're going to do in this lecture, or at least this mini lecture, is just to formalize things a little bit more. Okay, so I've already pointed out that it's the common common system of units throughout the world, pretty much. And what's important is you understand that there's a set of these things called base units. Here's a table showing you these base units. Some of these you probably won't come across in chemistry, particularly things like luminous intensity. Some of them, or most of these, you will. One of them you will come across in some later work that you do around the mole. In terms of temperature measurement, we don't use degrees C, Celsius. We actually use something called Kelvin in science. It's slightly different. Electric current amps, that's commonly used, and the other 3 here are pretty commonly used and you're familiar with them. So for example, we have the things when you're measuring length, of course, you measure them in units called meters, and they have a symbol associated with them. So for a meter it's a small m, for mass it's a kilogram, kg, times a second s, etc. Now the other sorts of units that you encounter in the SI system are derived units. These are probably not so familiar to you, but I'll just give you some examples. There are a couple that you'd come across. So this first one, for example, you'd come across when you measure area. Clearly you don't measure it in meters because that's a linear measurement. You measure it in square meters, and it's given a symbol as well in scientific notation, and it's m to the power of 2. That means m times m, if you like, m squared. For a cubic meter, obviously that's a measurement or a unit of measurement for volume, and hence it's looking at length, breadth and depth, and in that case of course it would be meters by meters by meters, or meters cubed. Here's some other examples for you to have a look at your leisure. I've got a little thing down here that says the formula for speed is equal to distance over time. Do the units in the table make sense? I'm just alluding to the fact here that the units that you get when you perform a calculation should be consistent with what you'd expect. So for example, speed and velocity, speed's measured in meters per second, there it is there, meters over seconds is meters per second, you can read that as. And do the units square up? You bet they do, because you would measure distance in meters, of course. So it would be meters here divided by the time. The time's measured in seconds, and you can see that the units that you would end up with would be meters per second. Now, because some of the derived units are actually quite long and complex looking, I think you could probably see that from the previous table, sometimes those derived units are encapsulated in their own name. So for example, when we measure force, the formula for force is mass times acceleration, which mass is measured in kilograms. There it is there. Just get my pen here again. There we go. It's mass times acceleration, and that's how you do indeed measure acceleration. The units are going to be meters per second squared. Now it's a bit of a mouthful to keep working out equations and then saying it's, for example, 5 kilograms meters per second squared. That's a very long way of saying it. So this set of units here is actually summarized by using another term, and that term is called newtons. So when someone says there's a force of 5 newtons, they actually mean 5 kilograms meters per second squared. Here's some other derived units. You can look at them at your leisure. None of this really is something that you are required to remember. Okay, now the other thing with SI units is that we can use prefixes to change the values of particular units. So let me just again, it's best to illustrate this by example. So if we have a look at, for example, these prefixes here, one of them you're already familiar with. If I get my pen here again, and just use a red one, okay, you know that there's a thing called a kilogram. That's a kg. Well, that kilo there is actually a prefix, and what it's referring to is this factor here. Now you mightn't be too familiar with these little superscripted numbers up here, but all this means is 1 followed by whatever the number of zeros is. So 10 to the 3 actually means 1 followed by 3 zeros, which is another way of saying 1,000. 10 to the 2 is 1 followed by 2 zeros, which is another way of saying 100. That's 1 followed by 1 zero, so that's actually 10. Okay, so you can see here that this is just a shorthand notation. I mean, once we get up here to say 10 to the 9, then we start talking about, I guess that would be a billion, but it's much clearer to use this notation because you know that it's 1 followed by 9 zeros. This one's 1 followed by 12 zeros. Over on the other side here, this is, if you like, the opposite way around. So this is where we've got a negative number here as a superscript. Say, for example, that one. That actually represents 1 over 1 followed by 2 zeros. So that's 100th. That's a 10th. That's a 1,000th. So you can see how these two are related, right? So that's 1,000. That's 1,000th. So how does it all fit together then? Well, for example, if we look over here in terms of everyday terminology, when we're talking about things like hard drive space on a computer, we might be thinking that our hard drive is, say, it's specified as, say, 500 gigabytes. Well, that's actually half a terabyte. Why is that? Well, 500 gigabytes, hang on, I'll start again. In 1 terabyte, you might be able to see there you've actually got 1,000 gigabytes. Why? Because it would be 12 minus 9 equals 3. 1 followed by 3 zeros is 1,000. So you can see the difference between these numbers is changing, at least here, by 1,000. Here it's changing by 1. So by using this system, you can actually get a handle on very, very large numbers or very, very small numbers just simply by using these prefixes. Just to give you another example, in the work that I do in molecular biology, I'm often measuring out volumes that are in microliters, so they're actually this value here, which is millionths, because that's 1 by 10 to the, but that's 1 followed by 6 zeros, and it's 1 over that value, of course, so it's 1 over a million, so it's a millionth of a litre. So it'd be very clumsy for me to keep saying it's 1 millionth of a litre. It's actually easier to just say I'm working with, say, a microliter. Anyway, I think you get the idea. You'll have to learn these prefixes. Again, rather than you sitting there trying to memorize them, as in some of the previous things I was talking about, one of the best ways to do it is to actually get in there and start working and doing problems, etc. And you'll become very familiar with using these prefixes very, very quickly. The other thing is, of course, you've got to learn to be able to interchange them. And again, that requires you doing the work and the problems. You can listen to me as much as you like, but the important point is that you actually do the study, the work and the problems. Okay, that's just another little example there for you. Alright, the last thing I want to point out, which I've alluded to some degree anyway, is that when you're working with these units, when you're doing calculations, it's important that you get the right units at the end of your calculation. So if you're multiplying units together, then you summarize them as some power here. Let me illustrate it again by example. Let's say that you're working out the volume of a cube, and you know the formula for volume of a cube is the side cubed, right? So I could write the formula here as the volume of the cube is equal to the side cubed, and if I were told, for example, that the cube is actually each side is 1 meter in length, then I can write or fill out the calculation here by saying, okay, well, it's actually 1 meter by 1 meter by 1 meter. What is my answer? Well, my answer is, well, let's look at the magnitude, which is the number here that we're interested in to start with. It's 1 times 1 times 1, which obviously equals 1. So there it is there. Right, so the magnitude is 1. And it's meters by meters by meters. In other words, it's meters cubed. So the units there are going to be meters cubed. I can't stress enough that if you're asked a question and you have to calculate an answer, if your answer simply has a magnitude and there is a unit of measurement associated with it, probably the best you can hope for in terms of marks for your answer is going to be half. It's a bit like me saying to you, I'm 187. That makes absolutely no sense unless I associate units with it. I'm 187 centimeters. I'm not 187 years old. But the two comments obviously have very, very different meanings depending on which units you're using. Okay, so again, I encourage you, make sure that you get stuck into the problems in the book of readings. The other thing is there is a mini tute associated with working with units, and I encourage you to have a look at that one as well. Okay, see ya.